Okay, guys, we are jumping into one of the more exciting sections of AP Pre-Calc, and that is talking about our periodic functions. We're getting into the trig portion of it, and so we're going to really hit hard on periodics right now because it's very important that y'all understand how a periodic function works, and then just the basic components of it. This might be one of the most applicable things we do. We've talked about linear functions, we've talked about exponentials, rationals, and logarithmic functions. This applies to so many real-world situations, and if you look at that initial paragraph there, it talks about different things that essentially they're periodic. You see a repeat of dependent variables, dependent values from independent values, and so it mentioned things like your breathing, your heartbeat, waves on the ocean. More things might be like Ferris wheels. All these things are periodic functions, and we're getting into where we're really going to be able to apply some of the math that we have to real world situations. But before we do that, it's important for you to understand a couple of basic terminologies when it comes to a periodic function. And essentially, what is a periodic function to begin with? And what that periodic function is, you have to see a repeat in y values. When you're talking about what is a periodic function, it's a function that repeats a pattern of y values over a regular interval. And the regular interval is a key part in order for it to be periodic. And so I want you to pay attention to that and understand that this repetition of y values, it has to happen at regular intervals. Um, and then when we go from that to a cycle, and what a cycle is, well, how long does it take for us to complete a pattern of those y values before we start to repeat again? And so we're going to do a lot of practice here with cycles and identifying what those are, and then from there being able to identify what we call as the period. And the period is nothing more than the horizontal length of one cycle. And so right off the bat, we're going to do some examples where all we do is we figure out what the period is. How long on the x-axis does it take us to repeat that cycle? And then finally, the last thing we're going to look at is going to be the amplitude. The amplitude is half the difference between the maximum and the minimum values. And so what we'll do is for amplitude, I want you to get used to using this function here. It's going to be 1/2 times the absolute value of the maximum value minus the minimum value. And so we're going to use that equation a lot to determine what the amplitude is. So let's take a look over here at the right. We have a graph, and you can see this is a periodic function because we repeat our y values. First thing I'm going to point out is we're going to look at how long is the cycle. So how long does it take us to run through one complete repetition? So if we start here at 0 and we travel along this line here with a highlighter, how long does it go until we complete one full cycle? So we go here and we're back to 0, but we haven't done a full cycle yet. We have to keep going until now we come back up, and at that point we've reached one cycle. Okay, so that would be one cycle here. And the period there, because if you look, we'll talk about this, so this distance here is going to be one cycle. And so how long did it take us on the x-axis to get back to the original point? Well, we went from 0 to 6. So what we would say is our period is equal to 6, because that's how long it took us to complete one cycle. Okay? And so now finally the amplitude. The amplitude is simply the distance, like I said, half the distance from the difference between the max and the min. And so you see this graph right here. This graph right here goes all the way up to 1 on the y-axis, and then it goes down to 1, -1, on the y-axis as well. So these two red lines that I just drew, they are your amplitudes. Okay, so that's an amplitude, that's an amplitude. So the amplitude for this particular periodic function is 1. But if we use the formula that I mentioned earlier, that would be a equals 1/2 times the absolute value of max minus min. Well, the max that it gets to is 1 minus the minimum it gets to is -1. Well, two negatives make the positive, and so we end up with 1/2 times 2, which equals 1. And so that would be our amplitude right there. So let's take a look at a couple of examples here. And what we have is, if we look at example 1a, we got a function. They want us to identify the one cycle in two different ways, which means we're just going to pick out two different starting points. And then we're going to identify what the period is. So if you look, again, I'm going to start here at the traditional origin, which is 0. So one cycle, we might say, would be from 0. And then again, it takes us all the way to 4 to get back to that starting point. I'm going to highlight, it takes us all the way from here. We got to go down here, repeat it, and then bam. So if you look along the x-axis, it takes us 4, okay? Now you could also say, well, what if we want to start it here and start at -3? Now I need to get back to the top here, which again, from -3, that red line now takes us to 1. So the second way we could identify it would be a cycle from, we went from -3 to 1. But either case, our period is 4, because that's how long it takes us to get back, from one starting point to the next starting point. Okay, if you look at example B, a little bit different looking graph here, but it's still a periodic function because we're repeating the y values. And so one way that I might represent the cycle is I might start here at, I don't know, let's start here, -2. And if I'm sorry, the x value is -1. And so what I can do is I can look to see how long does it take me to get back. Well, if we go here from -2, then we get back down, or sorry, -1, I keep making that mistake, -1 to 2. So that cycle would be -1 to 2. Another way, let's say we start, let me change my highlighter here. Let's say we start up here at the top. How long does it take me to get back? Well, I'm starting at -3. That's the x value. And if we go down and back up, that puts me at the origin, x equals 0. And so we run from -3 to 0. But again, if you look, our period is nothing more than the distance in between those two. We have a period of 3 there. Okay, period of 3. Okay, now let's look at whether functions are periodic or not. And again, remember the definition of periodic. The definition of periodic is, do my y values repeat? All right, and that's the key thing to look at here. So if you look right here at this, this is -4, -1. Okay, and then what happens is, let's go to the next one. That's -2, 0. Let's look at this one. That's 0, 1. We'll pick this one. That's 2, 2. And then we're looking at 4, 1 here, or excuse me, 4, 3. Well, remember the definition of periodic means that the y values have to repeat. Well, if you look at the coordinates I just wrote down, none of those repeat. The y values are not repeating. So this one would not be periodic. And some people will look at that and think, well, it has the general shape of a periodic function, but if you look, the y values are not repeating. However, if you look over here at example B, our y values do repeat. Okay, so this is a periodic function. Our y values are repeating. And from there, we can figure out what the actual cycle and the period is. Remember, how long does it take to get from one starting point to the next? So if I choose, say, here, and I go down, and how long does it take me to get back up to that point of a y value repeating? Well, look, the x value was -2 here, and it took me all the way to x equals 2 to get there. So our cycle is from -2 to 2, right? Our period then is 4. Now, that amplitude, that was kind of the last feature we talked about here. Remember the amplitude. Amplitude is nothing more then 1/2 times the absolute value of the max value, and we're talking, when we say max, we're talking about the y values, minus the min, again talking about the y values. So let's take a look here at this amplitude. The maximum y value that this function gets to is right here, max value of 1. Okay, and then the min value that we get down to ends up being -2. So if we're trying to find the amplitude A, we would say the 1/2 times the absolute value. The max value is 1 minus the min is -2. Remember, 2 negatives gives us the positive. That's 1/2 of the absolute value of 3. We have an amplitude of 1.5. Now, so if I'm doing this and I have an amplitude of 1.5, we have this new element called the midline. And that midline is just what it says. It's this blue line that I'm drawing here. This is your midline. That's the halfway point between the max and the min, which is for 1.5 here. So if my max was at 1, I go down 1 and then another 0.5. So we end up drawing that midline. That midline is actually at what we call -0.5. Okay, y equals -0.5. So if we look over here at this function, this one's got a little bit more complexity to it. But again, just identify the max value, which for us is 4. And then down here, the min, let's see what it's scaled at, 2. So that min is -2. So now again, the amplitude is 1/2. Absolute value, max minus min. So it's 4 minus a -2. Change here. That's 1/2 of the absolute value of 6. We have an amplitude of 3. So if you look, my max value was 4. If I want to draw that midline that we were talking about earlier, it needs to be 3 below the max or 3 above the min, which ends up putting us at 1. So we have a midline here where I'm drawing this dotted line, and that'll come into play more later on when we start getting into our trig functions. But there's your midline because we have an amplitude of 3. So that means from that midline, the max is 3 above the midline, and the min is 3 below, which was -2 there. So let's look at a real world problem down below. What it tells you is, we're talking about sound waves here, produced by periodic changes in air pressure. And so we want to sketch the graph of a sound wave with a period of 4. So remember what period means. That means the time on the x-axis that it takes for us to get back to the original y value, wherever we choose to start that. And an amplitude of 2. So remember, really the whole gap, because the amplitude is 2, the whole gap between our functions should actually be 4, if we think about it that way. And so one thing you have to do here is we're going to let you see our x-axis there goes 1, 2, 3, 4, 5, 6, 7, 8. But you see the period is actually 0.004. So we're going to manipulate this a little bit. And we're going to say the x-axis scale is going to be represented as 0.001 for every increase. So what really, let me finish this real quick. Like 1 on the x-axis really represents 0.001. Okay, and so if we start here at 0, now remember I told you the amplitude's got to be 2. So that means that we just need to go up, and again what needs to happen is we need to be back here both above the x-axis and below by 4, because we're doing 0.004 as our period. So what's got to happen is we got to go up 2 to this point, come back down to the x-axis at 2, and then come back down below because it's got to repeat. So what's going to happen is you're going to go up, you'll come back down, and then come back up, and what we've done is we've completed one period right there. And so now the second period is going to be done at 8, so over here, because we have a period of 0.004. So again what has to happen is we're repeating the y values, And so we repeat that process again. So then the second time through, I'm actually going to do it in a different color, is going to look like this. And there's two cycles through our period. So again, a period of 0.004. Our scale was changed a little bit, and we have an amplitude of 2. And so there we go. That's graphing a periodic function. Let's do another one. If we look at this one, we got to finish the table first. And what we're looking at here is we're looking at pedals on a bicycle that's being ridden, and the height of the pedal varies periodically as a function of time. So if you think about it, when you're pedaling a bicycle, you're just repeating the process over and over again. And so you look and see they broke up the times in quarter seconds. And then the height in inches, which is talking about the height of the pedal above the ground at certain times. And so you see at 0, the height of the pedal is 18 inches above the ground. And then from there, it starts to decrease, and we know it's a periodic function. So at the bottom, at 1 second, we're going to start going back up. So what's going to happen is we're going to repeat those numbers going back up. And so repeat the process. And there's my table of values. The y values are repeating, and we've completed one period. So the period of the function, for us to get back to, and for those of you struggling to understand what the period means, for us to get back to the y value we started at, if we started at 18, how long does it take us to get back to 18? Well, it takes us 2 seconds. And so our period for this function is 2 seconds. Remember, the amplitude is nothing more than 1/2 the absolute value of the max value minus the min. Well, the max for us is 18. The min is 6. Alright, and so what happens is 18 minus 6 is 12, and half of that is 6. So we have an amplitude of 6. Okay, and so if we graph this function for the first 5 seconds, we have our table of values here. So I'm going to zoom in just a little bit so we can see. We start at 0.18 right here. At 0.5 or 0.25, we drop down to 15. Then we drop down to 12. Then we drop down to 0.75 and 9. And I'm just graphing points off this table, guys. Things we've done it forever. And then 1.0 and 6 here. You go back up to 1.25. That repeats the cycle at 9. And then I'm just repeating my values here. And we're back to the top. So again, we look right there. Our period matches at 2 seconds. And then it says to keep going for 5, but for the sake of time, I'm going to stop there. But all you have to do is repeat the process. Now, I am going to talk about our amplitude real quick. Our amplitude is 6, which means the distance between our midline and our max should be 6. The distance between our midline and our min should be 6. And so if we think about it, 18 minus 6 is 12. 6 plus 6 is 12, so our midline is going to be right here all the way across the graph. And like I said, for the sake of time, I'm not going to finish graphing those points, okay? But what you would do is you just simply repeat the process. And so I'll get you started here real quick. And so this next point should be here, and that's at 2.25 and 15. And then again, I'm just really going down 3 and over 1 right here. And so we'll continue that function like this right here. And so I'll let you go on and do the 5 seconds, because I want to do example 6 real quick and then get into 1b. That's right, we have 1b as well. So a lot of good stuff here. Here's what we got here. Periodic function goes through 5 complete cycles in 4 minutes. So we want to figure out the period of the function. So if it takes us 4 minutes to go through 5 cycles, the way we figure out the period is we take our total time and we divide it by how many cycles do we get done in that time frame. So in 4 minutes we did 5 cycles. So to figure out that period, that means every period takes 0.8 minutes to do. It takes us 0.8 minutes to get through a period. and then there are 60 seconds because they want it in sorry, they want it in seconds. So we're going to multiply that by 60 seconds over 1 minute. So in seconds, our one cycle takes 48 seconds. Okay, 48 seconds there is the time it takes us to complete one cycle. One cycle in 48 seconds right there. So if you're ever given how many complete cycles you do in a certain time frame, take the time frame that we operated in and divide it by the number of cycles that we completed in that time frame. And then if it says for seconds, multiply that by 60 because there's 60 seconds in 1 minute. And so it tells us the period of a function is 8 seconds. How many cycles does it go through in 30 seconds? Well, that one's pretty straightforward. We got 30 seconds of work that we're doing, or whatever's happening, 30 seconds. And if we can complete a cycle in 8 seconds, we're going to divide it by 8. Well, 30 divided by 8 means we're not going to complete a full 4 cycles. We're actually going to get through 3 3/4. So that's 3.75 cycles. The amplitude of a periodic function is 2.5. So we're kind of changing gears here. The amplitude of that function is 2.5 and the minimum value is 0. What's the function's maximum value? Remember what I told you. The amplitude is the distance between the baseline, and I'm going to put this in layman's terms here. The amplitude is the distance between the baseline or midline, excuse me, I've been saying midline, and either the max or the min value. So if it's 2.5 as the amplitude, and we have a minimum value of 0, that means our maximum value is going to be 5 right there. Now if you want to think about it in terms of a function, we could say that a equals 1/2, and that's going to be the max, and we know the min to be 0. Well, if we solve that, the amplitude is 2.5, and we got 1/2 times the max minus 0. Multiply both sides by 2. We get 5 there. That equals our max value. So if we want to solve that algebraically, we can as well. Alright, so looking at 1b here, we've already talked about definition of a periodic function was where the y values repeat. We're going to generalize this into function form. Alright, and the function f is a periodic function of x if and only if, and that's key, if and only if, there's a number k for which f of x plus n times k equals the original f of x function. Okay? And a lot of that, you see that and you're like, what the heck does that mean? We're going to break down some problems here. The important thing to remember, though, when you're doing these, is that value of k is your period. So we talked about period in lesson 1a. So now k is the value of the period. So if we look at the first example here, what we have is what is the period k of the function. So if we look, remember periods, how long does it take for us to complete one cycle? So just picking a starting point. If I pick here, how long does it take my y value to get back to 3? Well, it started at -2. It took us all the way to 2 in order to get back to a y value of 3. So our period, which is k, from -2 to 2 is 4. So k equals 4. So complete the function behavior on the grid. Now we're just going to repeat the process here. And so to get from the max value, let's say, look at this, to get from the max value of 2 down to the minimum, that's a change of 1 in the x value. So if I start here at 6, that means I'm going to get all the way down here by 7. That's the change. And then if you look at the increase, it's taken 3x units to get back to the max. So if 7 is my starting point, it's going to take me all the way to 10 to get back there. So I'm looking at the x-axis and I'm seeing how long does it take me to get from the min to the max, and that's how I'm doing my graph there, guys. And so then again, if I start at 10, it's only taking me one x unit to get back to the minimum of 11. So by 11, I'm already back at the min here, just like that. And so we're complete the graph there. And so we've already mentioned that the period is 4. We want to show that f of x plus nk equals f of x. And so if n equals 1, what we have here is that we're starting, if we look at the very beginning of that graph, x starts at -5. And then we said the period, n is 1, and the period is 4. So that means if you simplify that, f of -1, and if you look right here, x is -1, what's the y value? Y value is -2, which is our minimum. Now let's do the next one, n equals 2. Again, start with the original x value, f of -5, but let's change this to 2, so that means 2 cycles through. Period is still 4. -5 plus 8 equals 3. If you look at x equals 3 right here, what's my y value? -2. So you see, instead of going through it, we can just figure out, and again, that n value is simply how many times we're going through each period right there. Looking at example 8, we're looking at temperatures in Austin, Texas. Now, you see, obviously, the x-axis is not labeled months. So with problems like this, just make sure you go through and you identify the months by their number. So that way we correspond it to the x-axis. And so what we want to do is, we were talking about the temperatures, and we're talking about, because this repeats every year, it's going to be a periodic function. So if we graph these values right here, looking at 1, we were looking at 63. So I'm going to zoom in a little bit so I can see the graph here. I've got the values over here to my left as well. And so 1 is at about 63. And if we plot these points, 2 is at 67. That's in February. Then in March it jumps up to 75. In April we jump up to 81, just above here. And then May we jump up to 87. June we jump up to 94. And then after that, July jumps all the way to 98, which is just below 100. And then finally in August, just like here, it jumps up to the hottest, which is 100. But then we start to see a decrease. We jump back down to 93. And these are just estimates, guys. And we jump down to 83. And then we jump to 72. And then finally we're looking at 64 for the month of December. And so there's our periodic function. If I draw a graph here, it's going to run through these points here. Now, that's how long it takes us to get back to our starting point. What it tells us is, it tells us to describe the period. Well, this one's pretty straightforward. You know, once you get through December, where do you jump back to? You jump back to January, but that takes 12 months. That's how long it takes us to repeat this. So it's 12 months or 1 year. And then the amplitude. Remember, amplitude is simply 1/2 times the absolute value of the max minus the min. Well, the max value we had was 100, so that's 1/2 times 100. The minimum value we saw was in January. That was 63 degrees. And so what happens is we're looking at an amplitude of 18.5. And so to find my midline, I'm going to take the minimum value here. And what I'm going to do is I'm going to take the minimum value, which was 63, and I'm going to add that 18.5 there. That's going to give me a midline of 81.5 here. You could have went max and subtracted as well, but I'm going to do that in a different color. We'll do a little black and red for dogs, all you dog haters out there. Too bad. So we're at 81.5, and so my midline is this black dotted line that I'm drawing just here. Okay? Alright, and so if we look at the next couple, look at example 9 here. We've got a periodic function, and we're going to look at now intervals of increase and decrease in concavities and vary rates of change. Okay, so if you look here, remember the period is how long does it take to repeat the y value, and if so, we look here, starting at this point, that's from -6, and it takes me all the way till 2 to get back to the original y value. So for a period, we go from -6 to 2. That's a distance of 8. So our period, and that's important here. Remember I told you that's going to be our k value. If you look here, our amplitude, the max value is 3, the minimum value is 3, and so the amplitude is just this distance right here. I'm going to show it to you graphically because we haven't done that in a while. Amplitude is 3. Just like that. Our max and our min value, remember when we say max and min, we're talking about what are the y values there. Well, the max that it gets to is 3. The min that it gets to is -3. We're just looking at y values there. What's the highest and the lowest it gets to? So when we talk about intervals of yours, let's see, that should say intervals of increase, intervals of decrease, and I apologize for that. And so this should say increase with your notes, and this should say intervals of decrease. No, I'm sorry, I'm looking at the wrong problem. Erase that. It does say concave up and concave down. I'm looking at the next problem. So let me erase this. Oh, it took away everything. Let me rewrite this. Sorry, folks. So the max is 3. The min was -3. But it does say concave up and concave down. So remember with concavity, that's talking about the rates of change increasing and decreasing. Remember, concave up means increase in rate of change. Concave down means decrease in rate of change. And so if we look here, what I'm going to do is I'm going to look for the first inflection point or a starting inflection point. And so what we're doing is the first inflection point I see that I want to work with is going to be right here. Right here where we change from increasing or concave up to concave down. Or excuse me, concave down to concave up. And so what we have here, if we're talking about concave up, that's the first time I start to see it. Remember with concavity, we always use parentheses, and we start with -4. Now, remember this function is going to continue to repeat past what we can see here on the graph. So what we have to do is we have to say, okay, -4, and this thing's going to repeat on a period of 8, because that's what we found in part A, times n. And then it's also, again, it's concave up, starting at up to here, and then from there to it stops being concave up at 0 plus 8n. And so what we've done, I'm going to highlight this in green, is we've highlighted where are we concave up, because it's x equals 0 there, you'll see we changed to concave down. Okay, and then what we say is, we say, all right, it's going to be that, let me erase that, for all values of n that exists. Okay, for all integers of n. Concave down then picks up. If you look right here for concave down, the first spot we see concave down in this graph is going to be actually over here at -8. And what happens is, if we highlight this in yellow, it's concave down until -4. So our interval of concave down is going to be from -8, but remember our period is 8, times the value of n until -4, and then the same thing. And again, that 8 is coming from the fact that that's the period. And again, that's for all integers of n. Okay. And so then it asks for the points of inflection here. Well, the first point of inflection where we see a change, if we wanted to do that, the first spot we see it change from concave down to concave up is at -4. So that would be x equals -4 plus 4n. So on the graph that we're given there, because that's where we see the first change of concavity, from concave up to concave down. So to recap, what we did for part D and part E was we mentioned where for concave up, where's the first interval that I see concave up? Well, that starts at -4 and then it stops at x equals 0. But then I got to remember this thing's going to repeat on a period of 8 endlessly. And so what we have to do is we have to take that into account. That's why we have the plus 8n there on the back ends of both of those. Same thing with concave down. Where do you first see concave down? Well, at -8. And so that's where we started, -8. But again, we have to take into account this will repeat. So it's plus 8n because our period is 8. All right. Same thing here with increase and decrease. Just remember increase and decrease. We use, what we do is we use brackets instead of parentheses. I'm going to jump through this one real quick because by now we should identify the period real well. The period here is 8 again, and the amplitude is 3.5. Okay, you can take some time there, go through and figure that out, make sure you do it right and check the answer. Our max value is 4. Our min drops down to -3. So now we're doing intervals of increase and decrease. So we got to use brackets. Now, again, the first spot that I start to see an increase is at x equals -2. So we're going to start with -2 plus, again, the period is 8, so it's 8n. But then it stops at -1 plus 8n, and we close that bracket off. Okay, so we start to see an increase there. Now I'm going to include a second one because if you look, we have two different levels of increase here. We have this one, but then this one increases more. So I need to include that one as well. And so remember what periodic means. It means the repetition of y values. And so it takes us all the way until 8 to repeat those y values. Okay, so that's why we have to include this one as well. So then that one starts at, again, brackets. That one starts at 2, and then it goes plus 8n, but then it stops at 3 plus 8n here. Okay, so again, you got to remember it's the repetition of y values, and a typical mistake is that first one, you get done with it, well, we still haven't repeated our y values. So there's two different intervals of increase within this period, within this cycle. Okay, so same thing with decrease. We start to see the decrease starting at -5, and it ends at x equals -2. And both of these are plus 8n. Again, the 8 comes from the fact that's our period. But again, repetition of y values, we've got to look and see that, whoops, so I had this first one decrease, but I still haven't repeated the y values. I got to include this one as well. And so picking back up at -1 plus 8n, and it stops at 2 plus 8n. And both of these are for all integers n, or for n that's in the set of integers. Now the average rate of change, this goes back to unit 1, but you see the average rate of change is different over every interval. So if we look, remember, average rate of change is the change in y over the change in x. So the average rate of change here from 2 to 3, if we look at x equals 2 to 3, from 2 to 3, that's a positive average rate of change, and it goes from -3 to 4, which is a gap of 7. So that's an average rate of change of 7. If we do the average rate of change from 3 to 6, going from x equals 3 which starts at a y value of 4, to 6, which is a y value of negative 3, what happens is, remember, it's the change in y over the change in x. That's going to be a change of minus 7 over a change of 3. Average rate of change there is negative 7/3. Average rate of change from 6 to 7. Again, our x changes by 1, so we can just look to see. From 6 to 7, we go from negative 3 up to 2, which is a change of 5. And then finally, our average rate of change from 7 to 10. We know it's a decrease, so it's going to be negative. If you look, it starts at 2, it goes down to negative 3. That's a change of minus 5 over 3. So we have an average rate of change of negative 5/3. So we're down to the last page here. We've got some real world problems. This was one earlier we touched on. You got a storm siren that's making 2.5 rotations per minute, and the sound waves have a radius of 1 mile. And so Mr. Tyler's house is 1 mile away from the siren, and the distance of the sound wave from his house varies periodically as a function of time. Okay, so we want to figure out if it makes 2.5 rotations per minute, okay, what's going to be our period? So remember, we take the time that it takes, which is 1 minute, and we divide it by how many rotations happen. Well, that's 2.5. So that's 0.4, but in seconds, which is times 60 seconds, it takes us 24 seconds. It takes us 24 seconds to get back to the starting point. Okay? And so 24 seconds is our period. And so what we're going to do is we're going to start here at 2, because we're facing due north. Alright? Let it be 0 to t equals 60. And so then 24 seconds is how long it takes us to get back to that starting point. So at 12 seconds, we're stuck at 0. And so it goes here and then back to here. And again, what happens is, again at 48, we're back, we finish up another period, another cycle. So we drop down at 36, we're at 0. Okay. And it's not showing here on this one, but on your notes, this is a key function, is the siren begins facing north. That's why I started it at 2. Okay, and so then of course your baseline is half the distance, or your midline. So this red dashed line here, there's your midline. Okay, so again, it took us, key thing there was figuring out the period. And so the amplitude is our sound wave, which is 1 mile. Okay, and so if you look at that y-axis, that's miles. And so what happens is that amplitude represents the distance from his house, which is 1 mile. Okay, last one here, the Ferris wheel problem. This is a really good one. It's 120 meters in diameter, and so the height of a compartment on the Ferris wheel, h, is a function of time t, and it takes 30 minutes to make 1 complete revolution. Okay, so there's our 30 minutes is our period. We want to figure out the height of the car where you enter the ride represent the height at time 0. Okay, so we're going to start this thing at 0, 0. Now the amplitude, 1/2 times the absolute value. The max that it's going to get is going to be 120 because the diameter is 120. The minimum is going to be at the ground, which is 0, which means our amplitude is 60. So what happens is, if we get into this Ferris wheel car at 0, 0, now remember it takes us 30 minutes to get back to the ground here. So that means the peak of our function is at 15 minutes, and we're at 120. Okay, and so our graph is going to look like this. Sorry about that, it didn't look quite periodic. I'll repeat again. But the midline, if you look, we just figured out the amplitude was 60. So our midline is going to be here at 60. Midline of 60. And so at what time does the Ferris wheel reach its maximum? We've already mentioned that. The maximum height is 120. And that takes place at 15 minutes. And if you just, to clarify this, the midline should have been, and my graph is a little inaccurate here, but 7.5, we're at a height of 60, and also at a time of 22.5, we're at a height of 60. So there you go. There's periodic functions, guys. Again, key takeaways: amplitude, cycle, period is how long it takes us to complete a cycle. And I hope this video helped you just a little bit.